Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Lesson 9, Logarithms. How many digits do you need? Okay, classwork opening exercise is just a couple of practice problems from Lesson 8. So pause the video, see if you can do these, and then we'll come back. So it says to evaluate what power of base 2 gives you 8. State your answer as a logarithm and evaluate it. So the way you should probably do this is it's a base 2 and 2 to the power of something equals 8. So I want to get the bases the same. So I'm going to reduce 8 down to 2. And 2 times 2 times 2 is 8, so that's 2 to the third. And when your bases are the same, your powers have to be the same, and therefore x equals 3. So the power of base 2 that gives you 8 is 3. Evaluate what power of base 5 gives you 625. State your answer as a logarithm and evaluate it. So first of all, I didn't state this as a logarithm. So you'd say log and base 2 of 8 equals. So this would be our logarithmic representation. Okay? Instead of saying what power, you just change it to log. So evaluate what power of base 5 gives you 625. So you would say the log base 5 of 625 equals. And in order to solve this, you say 5 to some power equals 625. 5 to some power equals 5 to the power of what? Well, 5 times 5 is 25. And 25 times 5 is 125. And 125 times 5 is 625. So that's a power of 4. So x equals 4. So the log base 5 of 625 equals 4. All right, exploratory challenge. Autumn is starting a new club with 8 members, including herself. She wants everyone to have a secret identification code made up of only A's and B's, known as an ID code. For example, using 2 characters, her ID code could be AA. So part A says, using A's and B's, can Autumn assign each club member a unique 2-character ID code using only A's and B's? Justify your answer. Here's what Autumn has so far. So if she has 2 A's, she could give Chris A, B. She could give Tia B, A. And she could give Jimmy B, B. Okay? And that's it. We're done. There's no other way to arrange 2 digits other than these 4. Okay? Okay, so obviously 2 digits is not enough for 8 people. So the answer is no, she cannot. Okay, so answering in a complete sentence, you'd say no, she cannot assign a unique 2-character ID code to each member. The only codes available are AA, BA, AB, and BB. And there are 8 people. So part B says, using A's and B's, how many characters would be needed to assign each club member a unique ID code? Justify your answer by showing the ID codes you would assign to each club member by completing the table above. Adjust Autumn's ID if needed. Okay, so I'm going to, obviously, if 2 doesn't do it, what do you try? You try 1 more. Let's try 3. So I'm going to switch to red to add to this. So I'm going to give Autumn another A. And I'm going to give Chris A, B, and Tia A, B, A, and Jimmy A, B, B. Okay. And that's it with just starting with A, B, A, B, A, B, B. And then we could have B, A, B, A, B, B, BBA. Let me put them in order. So I'm just moving the A throughout. BAA, BAB, BBA, and finally Scott will get BBB. Of course, the order doesn't matter, but there you have it, and therefore we would need 3 digits. So you would say you would need 3 characters in each ID code. A completed table is shown above. Students could assign one of the unique codes to any club member, so this is not the only possible solution. Your order doesn't matter, but it's just easier to not miss one if you move one of the values through the set. Okay, page 2 says, when the club grew to 16 members, Autumn started noticing a pattern. Using A's and B's, part 1 says 2 people could be given a secret ID code with 1 letter, A or B. Then if there were 4 people, they could be given a secret ID code with 2 letters, AA, BA, AB, BB. And 8 people, notice what's happening here, could be given a secret ID code with 3 letters. So every time we add a letter, we can double the number of people in the group. So if I go to 4, that could be 16. So there's part C. Complete the following statement and list the secret ID codes for 16 people. 16 people could be given a secret ID code with 4 letters using A's and B's. Okay. So in answering this, we would say 16 people could be given a secret ID code with 4 characters. Notice the original members have their original 3 character codes with an A added to the end. Then the new members have the original 3 characters codes with a B added to the end. So now they want us to make a list of number of or possible outcomes. So if we need 4, let's just use blue here. I'm going to start with Autumn being all A's. And the easiest way to do this so that you're not missing any is introduce the other letter first and leave the other 3 A's. And then move the B throughout and show all the possible outcomes with 3 A's and 1 B. So then B would move to the 2nd position. And then B would move to the 3rd position. And then B would move to the 4th position. Like so. So there are the 5 possible outcomes with 1 B. Then we would introduce 2 B's. Okay, distribute the 2nd B throughout and leave the 1st B where it is. Okay, so I just move the B to the right one. And then finally, I start moving the 2nd B over. So now A, B, A, B. And then move this B over to the 3rd position, and it will be A, B, B. So now that I have 2 B's, those are the possible outcomes of 2 A's and 2 B's. So it's BBAA, AAB, or I'm sorry, BBAA, BABA, BAAB, ABAB, AABB. And finally, we're going to introduce another B. So I'm going to write it as B, 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 A, and now think of it as the A moving to the left. So it's going to be B, B, A, B, B, A, B, B, A, B, B, B. Okay, and then finally, all B's. Alrighty. Okay, so then once I'm done, I'm like, okay, well, where's the last one? So I'm looking here and I have 4 B's. I have 1, 2, 3, 4 with 3 B's. I have 2 B's, 1, 2, 3, 4, 5. And I have 1, 2, 3, 4, 5, 4 with 1 B. I missed the most important one. ABBA, Mamma Mia, how did I forget ABBA? Okay, anyway, there's this 15 or 16 people with 4 letters. So it says to describe the pattern in words. What type of function could be used to model this pattern? Okay, so it says to describe the pattern in words and what type of function could be used to model this pattern. So the number of people in the club is a power of 2. The number of characters needed to generate a unique ID code using only 2 characters is the exponent of the power of 2. So if you have log base 2 of 2, that equals 1. Okay, so if you have going up to our prior, let's see. What this means is if you have 2 members, you need 1 digit, either an A or a B. If you have 4 members, you need 2 digits, AB, BA, AA, BB, and that will give you the 4 different codes. So then if you have 3 members, or if you have 8 members, you need 3 digits. And if you have 16 members, you need 4 digits. And this continues. So you can use a logarithmic function to determine how many digits you need for any number of group sizes. So a logarithm function could be used to model this pattern. For 16 people, you'll need a 4-character ID code because the log base 2 of the number of people in the group equals the number of digits required. Okay, page 3 brings us to exercises 1 and 2. And it says in the previous problems, the letter A and B were like the digits in a number. A 4-digit ID code for Autumn's club could be any 4 letters arrangements of A's and B's because in her ID system, the only digits are the letters A and B. Number 1, when Autumn's club grows to include more than 16 people, she will need 5 digits to assign a unique ID code to each club member. What is the maximum number of people that could be used in the club before she needs to switch to a 6-digit code, and explain your reasoning? So what we're basically saying is the log base 2 of a group more than 16. Okay, what is the maximum number of people that could be in the club before she needs to switch to a 6 ID code? So I need log base 2 of some number to equal 6. So 2 to the 6th power would give me some number. 2 to the 5th power would give me another number. So basically what we're doing is, since log base 2 of 32 is 5, and log base 2 of 64 is 6, she'll need to switch to a 6-digit code when the club grows to more than 32 members. Okay, because log base 2 of 5 is 32. So that is the maximum number of possible outcomes. And so then this would be the value for the next, when would we switch to 7 digits? So this should be actually a 5. So log base 2 of some number equals 5. That's 2 to the 5th power, which is 32 people in the group. Okay, if that makes sense. And then log base 2 of 64 equals 6. 6 digits are required for up to 64 people. And then obviously you would do it one more time to get to the next. When would you need a 7-digit code? And that would be when there were 128 members and so on. Okay, so number 2 says if Autumn has 256 members in her club. All right, so remember, this is just simply a log base 2 problem. And the number that we have in our club goes here. And this is our equation. How many digits would she need to assign each club member a unique ID code using only A's and B's? Okay, so it says show how you got your answer. So we know it's a log base 2. The number of people in our group is 256. So I want to know how many, what power of 2 will give me 256. So if I switch this to an exponential function, I get 2 to the x equals 256. I want my bases to be the same. So I say 2 to the x equals 2 to some power. 2 times 2 is 4, times 2 is 8, times 2 is 16. That's 4. 32, 64. Where's my hand? 64, 128, 256. 2 to the 8th. Okay. So therefore, x would have to equal 8. I would need 8 digits. So that's how you would show your work on this. So say she will need 8 digits because the log base 2 of 256 equals 8. All righty. All right. Example. 1,000 people. 1,000 peeps. All right. Right there. 1,000 people are given a unique identification made up of these digits 0 through 9. How many digits would be needed for each ID number? Okay, so we have 1,000 people. We're only using numbers 0 through 9. One digit's obviously going to only cover 10 people. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is 10 numbers, including 0. So one digit would be 10 people. 2 digits would bring us all the way out to 100 people. So notice what's happening. 1 would yield 10 people. 2 digits would yield 100 people, right? 0, 0, all the way out to 99 is 100 different numbers. 3 digits would give me 1,000. Okay, so 1,000 would require 3 digits. So you would say you would just need 3 digits. 0, 0, 0, 0, 0, 1, 0, 0, 2, all the way out to 999. That is 1,000 3-digit numbers. Okay, so number 3 says exercise 3 and 4. These are exercises. Pause the video, see if you can do them, come back and see how you did. So here's number 3. There are approximately 317 million people in the United States. Compute and use the log of, let me put commas in here. 1, 2, 3, 1, 2, 3, 100 million. Compute and use the log of 100 million and log of 1, 2, 3, 1, 2, 3, 1, 2, 3, 1 billion to explain why social security numbers are 9 digits long. So social security numbers are usually not usually, they are 3 digits dash 2 digits dash 4 digits. Okay, 3, 2, 4. We group them because it's a memory thing. Okay, we as human beings are better at remembering stuff if they're in groups. So 3, 2, 4 is a social security number, totaling 4, 5, 6, 7, 8, 9 digits. So there's approximately 317 million people in the United States. Compute and use log of 100 million and log of 1 billion to explain why social security numbers are 9 digits long. So what they're saying is if I say the log base 2 of 100 million, actually it's not base 2. We would just say that the log of 100 million, it says to use log of 100 million. Okay, I just need to read the directions, right? The log of 100 million equals, so some number to what power gives us that. Okay. So if we get our calculator out, getting large numbers here, let me just set it up. Okay, so my base in this problem is 10. How do I know that? Because 0 through 9 are 10 digits. If we were just using A's and B's, that was our 2 digits. But in this case, it's 10 digits, so our base is 10. And notice it just says log here. So I'm just showing you, just for instance, 2 to the power of 9 is only 512, but 10 to the power of 9 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 1 billion. Okay, that's this number here. All right. So what I'm pointing out here is if it just says log and there is no base number, we assume it to be a base 10. Okay, it's a base 10 system, log base 10 of this. So in math, just like the square root, we always assume it's a square root if there is no 2 number here. If that's not there, it's a 2. But if it's a cube root, there's got to be a 3. If there's a 4th root, it has to be 4, and so on. But if it's 2, we don't put anything because we assume it's a square root. Same goes with the log. If we have a log base 2 of some number, then we know that it's 2 to the power of something equals this number. But if it just says log of some number, then we know it's base 10. Make sense? Okay, so that's just something new that I wanted to introduce before we continued with this problem. So it is a base 10 function. So what I want to know is if I have 1, 2, 3, 4, 5, 6, that's 100 million. If I want to take the log base 10 of 100 million, then that would mean 10 to some number equals 100 million. And 10 to the 1 is 10. That'd give you 1 0. 10 squared is 100. That'd be 2 zeros. 10 to the 3rd, 10 to the 4th, 5th, 6th, 7, 8. So x would have to equal 8 to give us this. So log base 10 of 100 million equals 8. Add another 0 and you're adding another digit. So you're adding another number to what it's equal to, and it's not. So let me get this out of the way. And we know that the log of 100 million is 8, which is the number of digits needed to assign an ID number to 100 million people. And we know that the log of 1 billion is 9, which is the number of digits needed to assign an ID number to 1 billion people. The United States government will not need to increase the number of digits in a social security number until the United States population reaches 1 billion. And honestly, that is never going to happen. Why? Because if we triple our population, then you would assume that the world would triple their population. I don't think our planet could sustain that number of people. All right, last page of the lesson, page 4. It says there are many more telephones than the number of people in the United States because of people having home phones, cell phones, business phones, fax numbers, which are probably going away, but there's still some, etc. Assuming we need at most 10 billion phone numbers in the United States, how many digits would be needed so that each phone number is unique? Okay, so what we're going to do is, first of all, I'm going to write the number 10 billion. 10, that's 10,000, that's 10 million, and that's 10 billion. So there are 3, 4, 5, 6, 7, 8, 9, 10 zeros. The number of zeros tells you how many powers it takes to get base 10 up to that number, if that makes sense. Okay, so what you would say is, since it's 10 digits in a phone number, 0, 1, 2, all the way up to 9, that's 10 digits. This is a base 10. So you would say the log, and I don't need to write base 10 here, the log of 10 billion equals some number. So then off to the side here, I'd convert that into an exponential function. So it's the base would be x. Just kidding. The base is 10, it's not there. 10 to some power equals 10 billion. So then I'd rewrite this as 10 to the x equals 10 to what power gives me this? Well, 10 to the 1 is 1, 0. 10 squared, cubed, 4, 5, 6, 7, 8, 9, 10. So 10 to the 10th would give me 10 billion. And therefore, since the bases are equal, x has to equal 10. So what we would say here is, since the log of 10 billion equals 10, you would need a 10-digit phone number in order to have 10 billion unique numbers. Phone numbers in the United States are 10 digits long. If you divide 10 billion by 317 million, the number of people in the United States, that would allow for approximately 31 phone numbers per person. That is plenty of numbers for individuals to have more than one number, leaving many additional numbers for businesses and governments. But there's so many people on the planet. How do we have enough phone numbers for everybody who has a phone all over the world? Well, they have what are called country codes. So in the United States, the country code is 01. I am living in, actually 001. I am living in, and then you use a plus sign for a 0, so it's plus 01. So I live in Sicily right now, and the Italy country code is plus 39. And then, so the first digits give you the country. So when you're calling a really long number, in order to call a different country, you use a country code and then the phone number. And that's how phone systems know where the phone number is you're trying to reach. All right, page 5 brings us to the end of lesson 9. Go to your problem set.